Have you ever wondered why objects fall to the ground when dropped? What keeps us grounded on Earth instead of floating away? The answer lies in a fundamental force of nature: gravity. Sir Isaac Newton, a brilliant physicist, unveiled this mystery with his law of universal gravitation. Newton's groundbreaking idea revolutionized our understanding of the universe. He realized that every object in the cosmos attracts every other object with a certain force. This force, gravity, is responsible for holding the universe together, shaping galaxies, and even dictating the motion of planets. Newton's discovery wasn't just a stroke of genius. It was the result of years of meticulous observation and calculation. His law of universal gravitation remains one of the most fundamental laws in physics, laying the groundwork for centuries of scientific advancements. Newton's law of universal gravitation can be expressed through a simple yet elegant formula: F equals G m1 m2 over r squared. Let's break it down. F represents the force of gravity between two objects. m1 and m2 are the masses of the two objects interacting gravitationally. R is the distance separating the centers of these two objects. Finally, G is the gravitational constant. This formula tells us that the force of gravity is directly proportional to the product of the masses of the two objects. In simpler terms, the more massive the objects, the stronger the gravitational pull between them. Conversely, the force of gravity is inversely proportional to the square of the distance between the objects. This inverse square law means that as the distance between two objects increases, the gravitational force between them decreases rapidly. Imagine throwing a tennis ball and a bowling ball with the same force. The tennis ball, being lighter, travels a greater distance. The bowling ball, due to its larger mass, travels a shorter distance. This is a simple illustration of how mass influences motion. Now, let's apply this to gravity. The Earth, with its enormous mass, exerts a strong gravitational pull on us, keeping us firmly planted on the ground. The more massive an object is, the stronger its gravitational pull. This concept explains why we feel much lighter on the moon. The moon, having significantly less mass than the Earth, exerts a weaker gravitational pull, resulting in a lower apparent weight. Section 4. Distance is key. The force weakens as we move apart. Imagine holding a magnet close to a metal object. The magnetic force is strong, and the object might even jump towards the magnet. As you move the magnet away, the force weakens, and the object no longer feels the pull. Gravity behaves similarly. The closer two objects are, the stronger the gravitational force between them. As the distance increases, the force weakens rapidly. This is why astronauts in orbit around Earth experience weightlessness. They are not truly weightless, but the gravitational force acting on them is significantly weaker due to their distance from Earth. This principle of decreasing gravitational force with distance explains why planets farther away from the Sun have longer orbital periods. Section 5. G. The universal constant, a special number in the cosmos. In Newton's formula for universal gravitation, G represents a fundamental constant known as the gravitational constant. This constant plays a crucial role in determining the strength of the gravitational force between any two objects in the universe. The value of G is extremely small, approximately 6.674 times 10 to the power of -11 Newton meters squared per kilogram squared. This small value indicates that gravity is a relatively weak force compared to other fundamental forces like electromagnetism or the strong nuclear force. Despite its small value, the gravitational constant is incredibly important. It ensures that the laws of gravity apply consistently throughout the universe, from the smallest particles to the largest celestial bodies. Section 6. Gravity's everyday wonders, from tides to orbits. The effects of gravity are all around us, shaping our everyday experiences. The tides we observe in our oceans are a direct result of the gravitational pull of the moon and the sun on Earth's water. The moon's gravity pulls more strongly on the side of Earth facing it, causing a bulge in the ocean. This bulge creates a high tide. On the opposite side of Earth, the moon's gravitational pull is weaker, resulting in another bulge and a corresponding high tide. The sun also influences tides, but its effect is weaker due to its greater distance from Earth. The most dramatic tides, known as spring tides, occur when the sun, Earth, and moon align, combining their gravitational forces. Gravity also plays a vital role in keeping planets in orbit around stars. The sun's massive gravitational pull keeps Earth and the other planets in our solar system orbiting in predictable paths. Section 7. A universe governed by gravity. A lasting legacy. Newton's law of universal gravitation revolutionized our understanding of the universe. It provided a simple yet powerful explanation for why objects fall to the ground, why planets orbit stars, and how galaxies hold together. This law continues to be a cornerstone of modern physics, informing our understanding of black holes, the expansion of the universe, and the search for extraterrestrial life. Newton's work laid the foundation for Einstein's theory of general relativity, which further refined our understanding of gravity. The law of universal gravitation is a testament to the power of human curiosity and our ability to unlock the secrets of the universe. By understanding gravity, we gain a deeper appreciation for the intricate workings of the cosmos and our place within it.